Concrete building construction is like conducting a symphony with people, material, cranes, drawings, all try to play it in the same tone. But in reality, it often sounds more like a jam session with no sheet music. At the core of this chaos lays the particular characteristic of the concrete, which is unpredictable, sensitive to its environment, and once you put it, there's no undo button. Although we validate the material and structural integrity, it often happens in data silos. It's like checking each instrument separately without ever hitting the whole orchestra. This is where my thesis comes in. I'm exploring how digital twins can help us to make sense of this data mess. By integrating diverse sources of information, they hold the potential of streamlined validation processes and data-driven decision-making. To ground my research, I have worked in a real-world case study, the construction of an office building in Barcelona, where we collected measures for 6 twin applications. These are concrete temperature, laser scanning of slabs, GPS tracking of the hook, strains during slabs post-tensioning, accelerations during column vibration, and monitoring of task progression. This real-world laboratory raised 4 main research challenges: how we can generate interoperable digital twins data, which job roles and workflows do we need to make digital twins work on site, how we can connect structural simulations, and which type of system can help us to tie all this information together. And here is what has emerged. As you can see, my thesis is multi-layered as digital twins themselves. First, we developed a Grasshopper plugin, which is MatchFen, that allows the generation of 4D BIM, IoT monitoring, structural analysis, and data processing within the same unified parametric environment without jumping between applications. In addition, we defined workflows and job roles for digital twins in construction, along with the conceptualization of the digital twin manager as the director of the data orchestra. Moreover, we developed 2 data models to connect structural simulations into digital twins. One is OSAM, which is a JSON schema. The other is SSO, which is a RDF ontology. And finally, we developed a knowledge graph-based digital twin system that connects BIM, IoT, and structural analysis to enable real-time data-driven decision-making. We hope that these contributions help to a more productive building construction.